NASA revealed something traveling through our solar system right now that's so impossibly old. It existed before our planet, before our sun, before everything we thought we knew about cosmic beginnings. A comet billions of years old here now, and we might be the only generation that witnesses its arrival. Think about that for a second. While you're watching this video, while you're living your everyday life, an ancient visitor from another star system is passing through our neighborhood. Not a rock, not just another celestial body, but something that preserves within it the chemical signatures of a time when our solar system didn't exist. When the space where Earth would eventually form was just empty darkness. This object, designated 3I Atlas, has traveled distances so vast that our minds can barely comprehend them. And it's carrying information that could expand our understanding of how the universe works. Let me be clear. This is passive physical preservation, not intentional communication. You know what's remarkable about this? Scientists estimate this comet is somewhere between 3 and 11 billion years old. Let me put that in perspective for you. Our sun is about 412 billion years old. Our entire solar system, everything you've ever known, everything that has ever existed in human history, all of it formed after this comet was already ancient. This thing was already traveling through the cosmos when the cloud of gas and dust that would become our solar system was still just beginning to collapse under its own gravity. It existed during the formation of countless star systems. It persisted through the death of stellar populations, and now, by the orbital mechanics of a hyperbolic trajectory, it's here. But here's what keeps me up at night, and I think it'll keep you thinking long after this video ends. The timing of our detection of 3I Atlas raises an interesting question. How does probability work on cosmic scales? Here's what we need to understand. First, astronomical surveys have improved exponentially just in the last decade. Telescopes like Atlas now scan the entire sky multiple times per week. This isn't coincidence, it's technological improvement. Second, billions of comets exist in interstellar space. Statistical probability guarantees that some will pass through our solar system during our era. We notice them now because we finally have the technology to see them. Third, survivor bias affects our perception. We only recognize objects during windows when we're looking and when we have detection capability. If an identical comet had passed in 1950, we would never have known. The comet didn't choose to arrive. Now we develop the capability to recognize it. Now, think of it this way. If billions of people buy lottery tickets every week and someone wins the jackpot, we don't say the lottery was communicating with them. We understand probability. The same applies to interstellar objects. When our detection improves, we find objects. That's not cosmic messaging, that's how statistics works. If you're as fascinated by cosmic mysteries as I am, I need to know, where are you watching from? Drop a comment. And here's the question I'm burning to discuss with you. Do you think 3I Atlas's age tells us something we're not ready to accept about the universe? This discovery is too important to ignore. Hit like, subscribe, enable notifications, because the next interstellar object might arrive sooner than we think. What we're dealing with here isn't just another space discovery that scientists will analyze and file away. This is a fundamental challenge to the story we tell ourselves about our place in the cosmos. For generations, we've looked up at the stars and wondered if we're alone, if our solar system is special, if the formation of planets and the emergence of life is rare or common. 3I Atlas doesn't answer those questions directly, but it opens a door we didn't even know existed. It proves that our solar system isn't isolated. It demonstrates that objects older than our sun can wander in from the vast interstellar void, carrying with them the chemical signatures and physical properties of star systems that formed under completely different conditions than ours. The implications ripple outward in every direction. If this comet is billions of years older than our solar system, it formed in an entirely different era of the universe. The cosmos was younger then, still rich with the primordial elements forged in the Big Bang before generations of stars had lived and died to create the heavier elements we find in abundance today. The conditions under which 3I Atlas formed might have been radically different from anything we see in modern comet formation. And yet here it is, carrying that ancient chemistry right past our doorstep. What I find most striking is how this discovery arrived almost quietly. On July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, detected what initially appeared to be just another faint object moving against the background stars. But as astronomers gathered more data, as they tracked its trajectory and analyzed its composition, they realized they weren't looking at something from our cosmic neighborhood. They were looking at a visitor, the third confirmed interstellar object ever detected, and potentially the most significant one yet. Because unlike Oumuamua, which left scientists puzzled and divided, and unlike 2I Borisov, which behaved more predictably, 3I Atlas carries within it a chronological impossibility that forces us to rethink not just where it came from, but when it came from. And that changes everything. When you first hear that something is older than our solar system, your brain might accept it as an interesting fact, file it away, and move on. But I want you to really sit with this for a moment. Because the age of 3I Atlas isn't just a number. It's a doorway into understanding how profoundly different the universe once was, and how this single comet carries the memory of that ancient cosmos within its frozen body. Current evidence indicates that 3I Atlas formed somewhere between 3 and 11 billion years ago, with researchers proposing a median estimate of approximately 7 billion years. To understand what that means, we need to rewind the cosmic clock and imagine the universe as it existed then. 7 billion years ago, the universe itself was less than half its current age. Galaxies were younger, more chaotic, still violently forming stars at rates far exceeding what we see today. The Milky Way looked different. The very neighborhood of space where our sun would eventually ignite didn't exist yet in any recognizable form. Think about the implications of that timeline. When this comet formed in some distant stellar system, the cloud of gas and dust that would become our solar system was still scattered across a much larger region of space, not yet gravitationally bound, not yet collapsing into the rotating disk that would spawn the sun, the planets, and eventually us. The atoms that now make up your body, the oxygen you're breathing right now, the calcium in your bones, those atoms were still locked inside dying stars, waiting to be released in supernova explosions that hadn't happened yet. 3I Atlas existed in a universe where the materials necessary to build Earth hadn't even been manufactured yet. But here's where it gets psychologically disorienting. This comet didn't just form and sit still. It has been moving through the galaxy for all those billions of years. Imagine the journey. Picture this ancient body of ice and rock flung out from its parent star system by some gravitational interaction we can only speculate about. Drifting through the interstellar medium for time periods that dwarf all of human civilization. It passed through regions of space we'll never see. It witnessed stellar events that occurred billions of years before the first rays of sunlight ever touched the surface of Earth. It survived radiation storms, cosmic ray bombardment, impacts from interstellar dust particles traveling at incredible speeds. And through all of that, through billions of years of cosmic wandering, it preserved within its structure the chemical signature of its birth. That's what makes this discovery so extraordinary. Scientists theorize that by analyzing the composition of 3I Atlas, particularly the recent detection of hydroxyl gas, which is a signature of water, they can glimpse backward in time to understand the conditions that existed in whatever distant star system gave birth to this object. On October 28, 2025, the Neil Gehrels Swift Observatory detected that hydroxyl signature, confirming that this ancient wanderer carries water, the most essential ingredient for life as we know it, from an era when our own world didn't exist. Let that sink in. The water molecules locked in 3I Atlas are older than every ocean on Earth. They formed in clouds surrounding a star that lived and perhaps died billions of years ago. Those molecules have never known the warmth of our sun until now. As the comet swings through our solar system and begins to sublimate, releasing gases that scientists can detect and study, we're witnessing in real time the awakening of materials that have been frozen in deep space for longer than our planet has existed. Do you understand why this matters? It's not just about the age, it's about what that age represents. Every astronomical object we've ever studied in detail, every planet, every moon, every asteroid, every comet formed as part of our solar system story, they all share a common origin, a common timeline, a common chemical heritage. They're all siblings in a cosmic family that began roughly 4 billion years ago, but 3I Atlas is different. It's an outsider. It carries within it the evidence of a completely separate origin story, from a different time, likely from a different part of the galaxy, possibly from a star system that no longer exists. Preliminary data suggests that studying objects like this could revolutionize our understanding of how planetary systems form across different cosmic eras. The universe has been evolving chemically since the Big Bang. Early generations of stars were born with only hydrogen and helium, the primordial elements. When those stars died, they scattered heavier elements into space: carbon, oxygen, nitrogen, iron, all the building blocks of planets and life. Each generation of stars has enriched the galaxy with more complex chemistry. Our solar system formed from material that had been enriched by multiple generations of stellar death and rebirth. But 3I Atlas might come from an earlier chapter of that story, a time when the galaxy's chemical composition was noticeably different. What does that mean practically? It means this comet might have a different ratio of elements than anything we've seen in our own system. It might contain isotopes in unusual proportions. It might have minerals that formed under conditions we can't replicate in our laboratories because they require the specific circumstances of a younger, hotter, more energetic galaxy. Every measurement scientists take of this object is a measurement of how the universe has changed over cosmic time. And there's something deeply humbling about that, isn't there? We live in a moment, a flash in cosmic time, where we're conscious enough to recognize what we're seeing. We're the first humans who can point telescopes at the sky and identify visitors from other star systems. We're the first generation that can analyze their chemistry and read their history. Our ancestors looked up at comets and saw omens, portents, signs from the gods. We look up and see time capsules from epics of cosmic history we can barely imagine. Both perspectives inspire awe, but ours comes with the burden of understanding. We know what we're looking at. We know how impossibly rare this is. We know that 3I Atlas connects us, however tenuously, to a chapter of the universe's story that unfolded billions of years before our story began. So, when I say this comet is older than our solar system, I'm not just talking about a number. A time capsule from deep cosmic history, from the ancient cosmos, from a universe that was younger and stranger than the one we inhabit. Now I'm talking about an object that has survived longer than our entire planetary system has existed and has traveled distances so vast that light itself would take thousands of years to cover them. And somehow, against all odds, it's here right now, passing through our neighborhood, giving us a glimpse into a past we could never otherwise access. That's not just interesting, that's profound. That changes the way you look at the night sky, because now you know the universe is far more connected, far more dynamic, far more ancient and complex than it appears from our brief human perspective. Close your eyes for a moment and try to imagine traveling for 7 billion years. Not 7 days, not 7 years, 7 billion years. The number is so large that it loses all meaning to the human mind. The entirety of recorded human history spans maybe 10,000 years. Modern humans have existed for perhaps 300,000 years. The dinosaurs walked the Earth for roughly 165 million years. And yet all of those timescales combined represent just a tiny fraction of how long 3I Atlas has been on its journey through the cosmos. Where did this ancient wanderer begin its travels? That's the question that haunts every astronomer studying this object. And the honest answer is we don't know. We may never know with certainty, but studies propose some fascinating possibilities based on the comet's trajectory, velocity, and the physics of how objects escape their home star systems to become interstellar nomads. Current evidence indicates that 3I Atlas entered our solar system from a specific direction in space, moving at speeds that confirm its interstellar origin. It's important to understand that all data about 3I Atlas is publicly available and transparent. Every observation from ground-based telescopes, from space-based observatories like the Neil Gehrels Swift Observatory, from universities in NASA, has been published in peer-reviewed journals or released through official press releases. The discovery was announced publicly on July 1st, 2025, immediately upon detection. There is no hidden information waiting to be revealed. Science operates through transparency and peer review. If NASA discovered something extraordinary about this comet, it would be published immediately, just as it always has been. Transparency is not just an ideal in astronomy. It's the fundamental operating principle. Unlike comets born in our own Oort cloud, that vast sphere of icy bodies surrounding our sun at enormous distances. 3I Atlas carries a velocity and trajectory that clearly mark it as an outsider. It's moving through our solar system on a hyperbolic orbit, meaning it's not gravitationally bound to our sun. It came from somewhere else. And after swinging past the sun, which it did on October 30th, 2025, reaching its closest approach, or perihelion, it will leave our system entirely, continuing its eternal journey through the galaxy. But tracing that trajectory backward through space and time is extraordinarily difficult. The galaxy itself is in constant motion. Stars orbit the galactic center at different speeds, depending on their distance from the core. The spiral arms rotate, though not like a solid disk. Over the course of billions of years, the positions of stars shift dramatically. The star system where 3I Atlas formed, if that star even still exists, might be thousands of light years away from where it was when the comet began its journey. It's like trying to determine where a leaf in a river came from after it's been floating downstream for millennia, while the entire landscape around the river has been transformed by geological forces. Researchers theorize that 3I Atlas was probably ejected from its home system through gravitational interactions, most likely with giant planets. This is how astronomers believe most interstellar objects begin their wandering. In our own solar system, Jupiter acts as a kind of cosmic goalkeeper. Its massive gravitational field sometimes deflecting comets and asteroids that stray too close. Sometimes those deflections send objects crashing into the sun or other planets, but occasionally the interaction gives an object just the right speed and direction to escape the solar system entirely. If that object is moving fast enough to exceed the system's escape velocity, it becomes an interstellar traveler doomed or perhaps freed to wander the galaxy forever. Imagine being that comet. One moment you're in a stable orbit around your parent star, part of a cosmic family bound by gravity to a system you've circled for millions or billions of years. Then, in a cosmically brief encounter, you pass too close to a giant planet. The gravitational forces wrench you from your orbit, accelerate you to incredible speeds, and fling you outward into the darkness between stars. Within a relatively short time by astronomical standards, your home star fades to just another point of light among billions. You're alone, surrounded by the vast emptiness of interstellar space, and you remain alone for billions of years. The distances between stars are almost impossible to comprehend. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. That means light traveling at nearly 300,000 kilometers takes 4 years to bridge that gap. 3I Atlas has been traveling through space for billions of years, but even at interstellar speeds, it has likely encountered very few stellar systems during that time. Space is almost incomprehensibly empty. For most of its existence, this comet has been utterly alone, drifting through the void, surrounded by nothing but the faint glow of distant galaxies and the cosmic microwave background radiation left over from the Big Bang. What does that journey do to an object? Physically, we're beginning to understand. The surface of 3I Atlas has been bombarded by cosmic rays, high-energy particles from supernova, and other violent cosmic events for billions of years. This radiation alters the chemistry of the surface layers, breaking molecular bonds, creating new compounds that don't form under the gentler radiation environment of a planetary system. Interstellar dust particles, though incredibly sparse, occasionally impact the comet at relative speeds that can be tremendous, gradually sandblasting its surface. Without the protection of a star's magnetic field, without the relative safety of being part of a solar system, an interstellar object endures conditions that are harsh beyond our everyday experience. Yet somehow, 3I Atlas survived intact. It didn't fragment. It didn't collide with anything large enough to destroy it. It navigated the gravitational fields of passing stars without being captured or torn apart. Do you realize how fortunate that is? How many potential disasters it avoided over billions of years? The galaxy's full of hazards, rogue planets, dense molecular clouds, close encounters with other stars, passages through regions of intense radiation. Any one of those could have ended this comet's journey long before it ever approached our solar system. But it survived, it endured, and against all odds, its path through the galaxy eventually intersected with ours. That intersection wasn't guaranteed. The galaxy is vast, and the odds of any particular interstellar object passing through any particular star system are vanishingly small. Yet here we are. Some astronomers estimate that interstellar objects might pass through the outer reaches of our solar system more often than we realize, perhaps several per year. But they're incredibly difficult to detect unless they come close enough to the Sun to develop a visible coma or tail. 3I Atlas did come close enough. On October 30th, 2025, it reached perihelion, its closest approach to our Sun, and the Sun's heat began to vaporize the ancient ices on its surface, creating the telltale signature that telescopes could detect. Preliminary data suggests that by the time we detected it in July 2025, it was already well into our solar system, inbound toward the Sun. Astronomers had a relatively brief window to observe it, gather data, and try to understand what they were seeing before it whipped around the Sun and began its outbound journey. That urgency drove an incredible international effort. Telescopes around the world, both ground-based and space-based, turned their instruments toward this visitor. Every observation, every spectrum, every image was precious, because once 3I Atlas leaves our solar system, we'll never see it again. It will return to the darkness between stars, continuing its billion-year wandering through the galaxy, carrying with it all the secrets we weren't able to extract during its brief passage through our neighborhood. But here's what strikes me as almost poetic about this journey. For billions of years, 3I Atlas traveled in silence and solitude, unobserved, unknown. It existed in a state of cosmic anonymity, just another speck of frozen material, adrift in the vastness. Then, for a few brief months in 2025, it became one of the most scrutinized objects in the entire solar system. Humanity's most advanced instruments focused on it. Scientists analyzed its every characteristic. Its existence mattered deeply to thousands of researchers and millions of people around the world who heard about it. And soon it will return to anonymity. slipping back into the darkness, its moment of attention fading as it continues its endless voyage. There's something profoundly moving about that arc, isn't there? It reminds me that significance is contextual, that even the most ancient and well-traveled wanderers in the cosmos can have their moment of recognition, however brief. It also reminds me how much we miss. How many interstellar visitors have passed through our solar system undetected throughout history? How many ancient messengers drifted past before we have the technology to see them? How many more will we miss in the future because they don't come quite close enough, or don't brighten enough, or simply pass when our telescopes happen to be pointed in the wrong direction? 3I Atlas is extraordinary, not just because of what it is, but because we happen to see it, to recognize it for what it represents, and to understand even partially the magnitude of its journey and its age. That conjunction of the ancient and the contemporary, of the cosmic and the human, is where the real magic lies. On October 28, 2025, something remarkable happened that most people never heard about. The Neil Gehrels Swift Observatory, a space telescope designed to detect gamma-ray bursts and study transient astronomical phenomena, turned its instruments toward 3I Atlas and detected the spectral signature of hydroxyl gas, OH molecules surrounding the comet. If you're not a chemist or astronomer, that might sound like a technical detail, interesting, but not particularly meaningful. But let me explain why this detection is actually one of the most significant aspects of this entire discovery, and why it opens doors to understanding not just this particular comet, but the fundamental chemistry of star systems across different cosmic eras. Hydroxyl gas is created when water ice on a comet's surface is heated by the sun and sublimates, transitions directly from solid to gas without becoming liquid. As water molecules H2O are released into space, they're bombarded by solar ultraviolet radiation, which breaks some of them apart into hydroxyl OH and hydrogen. The presence of hydroxyl is therefore a direct indicator that the comet contains water ice. And water, as you probably know, is fundamentally important, not just as a resource, but as a key ingredient in the chemistry that makes life possible. But here's what makes this detection extraordinary in the context of 3I Atlas. This is water that formed in a completely different star system, likely billions of years before our solar system existed, under conditions that may have been significantly different from those that prevailed when Earth's oceans formed. This isn't our water. It's not even our generation of water, cosmically speaking. It's water from another time, another place, carrying within its molecular structure the chemical signature of a star system we'll never identify. Think about what that means for a moment. Water is composed of hydrogen and oxygen. The hydrogen in that water is primordial. It's been around since the Big Bang, virtually unchanged for 13.8 billion years. But the oxygen is different. Oxygen is forged in the cores of massive stars and released into space when those stars explode as supernovae. The oxygen in the water of 3I Atlas was created by a star that lived and died in the ancient universe, possibly long before our sun was born. That oxygen was then incorporated into a cloud of gas and dust that collapsed to form a new star system, the one where this comet originated. And now, billions of years later, we're detecting the signature of that ancient water as it vaporizes under the heat of our sun. Current evidence indicates that the chemical composition of comets can tell us about the conditions in the protoplanetary disk where they formed the rotating disk of gas and dust surrounding a young star from which planets and other bodies coalesce. Researchers proposed that different regions of a protoplanetary disk have different temperatures, pressures, and chemical environments, which affect what kinds of molecules can form and survive. By analyzing the precise chemistry of 3I Atlas, particularly the ratios of different isotopes and the presence of various molecular species, scientists can theoretically reconstruct aspects of the environment where it formed. Why does that matter? Because every star system is unique. The exact composition of the original gas cloud, the mass and temperature of the star, the dynamics of how the protoplanetary disk evolved. All of these factors create subtle but significant differences in the chemistry of the bodies that form. Our solar system's chemistry reflects the specific conditions that existed 412 billion years ago in our particular corner of the galaxy. But 3I Atlas formed under different conditions, possibly when the galaxy had a measurably different overall chemical composition. By comparing the chemistry we detect in this comet to the chemistry we know from our own solar system's comets, we can begin to understand how planetary system formation varies across time and space. Let me give you a concrete example of why this is so powerful. Studies propose that the ratio of deuterium to hydrogen in water can reveal the temperature at which that water formed. Deuterium is a heavier isotope of hydrogen with 1 proton and 1 neutron in its nucleus instead of just 1 proton. In colder environments, molecules containing deuterium form more readily relative to their regular hydrogen counterparts. So by measuring the deuterium to hydrogen ratio in the water from 3I Atlas, scientists can estimate the temperature of the region where the comet's ice formed. If that ratio is significantly different from what we see in comets from our own system, it tells us that the temperature conditions in that ancient protoplanetary disk were different from ours. Now extend that logic to other molecules. Comets don't just contain water, they also contain carbon dioxide, carbon monoxide, methane, ammonia, and a host of more complex organic molecules. Each of these has its own formation history, its own dependence on temperature, pressure, and the availability of raw elements. Preliminary data suggests that by building up a complete chemical profile of an interstellar comet, we can essentially peer into the formation environment of an alien planetary system, one that may no longer exist from billions of years ago. It's like finding a perfectly preserved fossil that tells you about an extinct ecosystem. Except in this case, the fossil is billions of years old and comes from a star system we'll never see. Do you see why astronomers are so excited about this? It's not just about finding water on a comet. We've known for decades that comets contain water. It's about finding water that originated in a completely separate cosmic context and using that water and all the other chemicals we can detect as a Rosetta Stone to decode the history of planetary system formation across the universe. There's also a deeper philosophical dimension to this discovery that I think deserves attention. The fact that 3I Atlas contains water, the same molecule that fills our oceans and enables life on Earth, reinforces the idea that the chemistry of the universe is fundamentally unified. The laws of physics and chemistry that operate here operate everywhere. The same molecular bonds that hold together water molecules in your body also held together water molecules in a completely different star system billions of years ago. There's something comforting about that, isn't there? Despite the vast distances and enormous timescales, despite the fact that we're separated from 3I Atlas origin by billions of years and possibly tens of thousands of light years, we're still connected by the same underlying chemical reality. And that connection raises tantalizing questions about life itself. If comets formed in ancient star systems carry water and organic molecules, the building blocks of life as we know it, then the ingredients for life have been distributed throughout the galaxy for billions of years. When stars form, when planets coalesce, when conditions become right, those ingredients are already there, delivered by interstellar comets and asteroids. The water in Earth's oceans didn't all form locally. Some of it was likely delivered by comets and icy asteroids billions of years ago. What if some of that water came from interstellar visitors like 3I Atlas? What if the chemical seeds of life on Earth have an origin story that extends beyond our solar system, back into the ancient cosmos? Researchers theorize that this process of chemical mixing of interstellar material entering solar systems and potentially seeding them with complex molecules might be far more common than we previously thought. If so, then the emergence of life might not be confined to individual isolated star systems. Instead, it might be a galactic phenomenon, with the chemistry of life spreading gradually through space over cosmic timescales carried by wanderers like 3I Atlas. I need to be very precise here, because this is where speculation can turn into misconception. While it's true that interstellar objects can transport organic molecules and water, the chemical building blocks of life, we have no evidence that Earth's life originated this way. This is crucial. The dominant scientific model, supported by the evidence we have, is abiogenesis. Life emerged from non-living chemistry in Earth's early oceans. Panspermia, the idea that life or its precursors came from space, remains a minority hypothesis without direct evidence supporting it. What 3I Atlas shows us is that material exchange is physically possible. It demonstrates that organic molecules can be transported between star systems, but material exchange is not the same as life origin. The distinction is critical. 3I Atlas carries water and organic compounds. Yes, but that tells us about the possibility of chemistry spreading through space, not about where Earth's life came from. Our best evidence still points to local origin through chemical evolution. That's a profound shift in perspective. It means we're not just products of our solar system's unique history. We're potentially connected to a much larger, older story of chemistry and possibility that spans the entire galaxy and reaches back to the earliest generations of stars. Here's something that should make you pause and think. 3I Atlas. This ancient messenger carrying secrets from billions of years ago nearly passed through our solar system completely unnoticed. If not for the Atlas survey telescope in Rio Hurtado, Chile, which happened to be scanning that particular region of sky on July 1st, 2025, we might never have known it was here. And even after its detection, the window for observing it was remarkably brief, constrained by the comet's trajectory, its relatively faint brightness, and the limitations of our current technology. Think about what that means. This is the third confirmed interstellar object ever detected in human history. The first one-eye Oumuamua was discovered in 2017, and by the time astronomers realized what it was and began serious observations, it was already outbound, leaving the solar system. They had only a few weeks of useful data collection before it faded from view. The second 2I Borisov was discovered in 2019 and provided a longer observation window because it was detected earlier in its approach. But even with improved detection methods and growing awareness that interstellar objects might be more common than previously thought, 3I Atlas still came dangerously close to escaping our notice. The problem is one of visibility and scale. Space is enormous, and even within our own solar system, there's vastly more empty space than there are objects to see. Comets, unless they're actively producing a bright coma and tail from solar heating, are extremely faint, just small chunks of ice and rock reflecting a tiny fraction of the sunlight that falls on them. 3I Atlas, even at its brightest during perihelion passage on October 30th, 2025, only reached an apparent magnitude of somewhere between 12 and 14. To address a concern that often arises, no 3I Atlas does not pose any threat to Earth. Its closest approach to our planet brought it to approximately 1.8 AU from Earth. That's 1.8 times the distance between Earth and the Sun, or roughly 270 million kilometers. It cannot and will not impact Earth. The object is on a hyperbolic trajectory, meaning it will swing around the Sun and then depart our solar system entirely, never to return. This is not a near-Earth object. This is a safe, distant visitor that we're fortunate to be able to study from our secure location. To put that in perspective, the human eye can see stars down to about magnitude 6 under perfect dark sky conditions. Magnitude 14 is roughly 4,000 times fainter than that. You need a decent telescope just to see it as a faint speck, and you need to know exactly where to look. That's where survey telescopes like Atlas become critical. Atlas, the Asteroid Terrestrial Impact Last Alert System, wasn't designed specifically to find interstellar objects. Its primary mission is to scan the sky repeatedly, looking for asteroids that might pose a threat to Earth. But in the process of doing that work, it images huge swathes of sky every clear night, and sophisticated software compares new images to previous ones, looking for anything that has moved or changed. When 3i Atlas appeared in those images, moving against the background of stars, it was flagged as something worth investigating. Follow-up observations by other telescopes confirmed its unusual trajectory, and gradually, over days and weeks of additional data collection, astronomers realized they were looking at something extraordinary. But here's the uncomfortable truth. We're still not very good at this. Current evidence indicates that many interstellar objects probably pass through the solar system undetected. Some are too small to see. Some move along trajectories that don't bring them close enough to the sun to develop visible comae. Some simply pass through regions of sky that aren't being monitored when they're at their brightest. Studies propose that for every interstellar object we detect, there might be dozens or hundreds that we miss entirely. That's a sobering thought, isn't it? The universe is sending us messages, delivering time capsules from ancient star systems, and we're only catching a tiny fraction of them. And even when we do detect an interstellar visitor, our ability to study it is frustratingly limited. By the time 3i Atlas was confirmed as interstellar, it was already well into its passage through the inner solar system. Scientists had to scramble to schedule telescope time, coordinate observations across multiple facilities, and prioritize which measurements were most important. There's always a tension between the desire to gather as much data as possible and the practical constraints of telescope availability, weather, funding, and the object's rapidly changing position in the sky. By November 2025, 3i Atlas was already past perihelion and heading outbound, gradually fading as it moved away from the sun, and its icy surface stopped sublimating as vigorously. The window for ground-based optical observations was closing. Space-based observatories like the Neil Gehrels Swift Observatory could continue tracking it for somewhat longer, but even they have limits. Eventually, within months, 3i Atlas would become too faint even for our most sensitive instruments, and it would slip back into the darkness from which it came, its secrets only partially revealed. Does that bother you? It bothers me knowing that this ancient object, this tangible piece of cosmic history, is slipping away from us. And we've only managed to capture a fraction of what it could tell us, knowing that future generations will look back and wish we had better instruments, more funding, more time to study it. Knowing that by the time we develop the technology to truly interrogate an interstellar visitor, to send probes to intercept it, to land on its surface, to bring samples back to Earth, 3i Atlas will be long gone, trillions of kilometers away, forever beyond our reach. This is the cruel irony of astronomy. The universe presents us with opportunities to learn, but those opportunities are constrained by time and technology. We're living in an era where we're just beginning to develop the capability to detect interstellar objects, but we're still far from being able to study them comprehensively. It's like being given a glimpse of a treasure room before the door closes. You see enough to know how much is there, but not enough to truly understand it all. Researchers theorize that this situation will improve. New survey telescopes coming online in the next decade, like the Vera Rubin Observatory, with its legacy survey of space and time, will scan the sky more frequently and more comprehensively than anything we've had before. They'll detect fainter objects, track faster-moving targets, and give us earlier warning when interstellar visitors arrive. That early warning is crucial because it provides more time to organize follow-up observations, to study the object while it's still bright enough to analyze in detail, and potentially even to plan rapid response space missions to intercept it. But for 3I Atlas, those future capabilities come too late. We got lucky that we saw it at all. We got lucky that enough telescopes were able to observe it during its brief bright phase to gather valuable data. And we got lucky that it passed close enough to the sun to sublimate and reveal its water-rich composition. But luck is not a strategy. If we're serious about understanding interstellar objects, about using them as windows into the formation and evolution of other planetary systems, then we need to invest in better detection, better tracking, and better rapid response capabilities. Because the next visitor might be even more interesting than 3I Atlas, or it might pass by even more quickly, and we'll only get one chance to learn from it. The universe doesn't offer reruns. When these ancient messengers arrive, we either seize the opportunity or we lose it forever. And that reality should drive us to do better, to see more clearly, to reach further into the cosmos, to grasp the knowledge that's being offered to us by these wandering time capsules from the ancient universe. To truly understand the significance of 3I Atlas, we need to place it in context by comparing it to the only other two confirmed interstellar objects that have visited our solar system: 1I, Oumuamua, and 2I, Borisov. Each of these visitors has been extraordinary in its own way, but each has also raised different questions and challenged our understanding in unique ways. Together, they're beginning to paint a picture of what interstellar space contains and how diverse these ancient wanderers might be. Let's start with 1I, Oumuamua, because it was the first, and it captured the public imagination in ways that no astronomical discovery had in years. Detected in October 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua, a Hawaiian word meaning scout or messenger from afar, was immediately recognized as unusual. Its trajectory clearly indicated it came from outside the solar system, but its physical characteristics were baffling. It appeared to be elongated, perhaps cigar-shaped, tumbling end over end as it moved. It showed no signs of a cometary coma or tail, suggesting it might be rocky rather than icy, more like an asteroid than a comet. But then, as it left the inner solar system, it exhibited a slight but measurable acceleration that couldn't be explained by gravity alone. That unexplained acceleration sparked enormous scientific debate and inevitably wild speculation. Now, I want to be clear about something important. Most scientists agree that outgassing is the most likely explanation for Oumuamua's acceleration. When volatile materials on a comet's surface are heated by the sun, they sublimate and release gas, creating a small but measurable thrust. This is well understood physics and happens routinely with known comets. The reason we didn't directly detect the gas from Oumuamua is not because it wasn't there. It's because our instruments at the time weren't sensitive enough to detect such a faint signal from such a distant object. That's a limitation of observation capability, not evidence of alien technology. The exotic explanations, solar sails, alien probes, technological artifacts remain highly speculative and lack supporting evidence. Science progresses by applying Occam's razor. When multiple explanations exist, the simplest one consistent with evidence is usually correct. For Oumuamua, that's natural outgassing. Some researchers propose that outgassing, the release of volatile materials from the surface, could account for the acceleration even though no gas was directly detected. Others suggested more exotic explanations, ranging from unusual internal composition to, in a few provocative papers, the possibility that Oumuamua was not entirely natural, perhaps a piece of alien technology, a solar sail, or derelict spacecraft. That speculation, while scientifically marginal, captured headlines and imaginations worldwide. But the honest truth is that we simply didn't get enough data on Oumuamua to answer most of the questions it raised. By the time astronomers realized what they were seeing and began intensive observations, it was already leaving the solar system. It was never particularly bright, and it faded quickly as it receded. Within a few months, it was beyond the reach of even our largest telescopes. We got enough data to confirm it was interstellar and to measure its basic trajectory and some rough physical characteristics. But much of what Oumuamua really is remains unknown. It left us with more questions than answers, and that uncertainty is part of why it remains so intriguing. Then came 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using a telescope he built himself. If Oumuamua was the mysterious stranger who showed up at the party, behaved oddly, and left before anyone could really get to know them, then Borisov was the polite, somewhat predictable guest who arrived, behaved more or less as expected, and gave everyone plenty of time to chat. Borisov was clearly a comet. It developed a bright coma and tail as it approached the sun, just like comets from our own solar system. Spectroscopic analysis showed it contained cyanide and diatomic carbon molecules commonly found in comets. In many ways, it looked remarkably similar to the comets we're familiar with, which was both reassuring and slightly disappointing. Reassuring because it suggested that comet formation might be a fairly universal process, producing similar objects in different star systems. Disappointing because it didn't challenge our understanding the way Oumuamua had. But Borisov still offered valuable insights. Researchers proposed that its chemical composition, while familiar, showed subtle differences from solar system comets, suggesting it formed in a colder or more carbon-rich environment than typical comets in our Oort cloud. It also provided the first opportunity to track an interstellar comet through its entire perihelion passage, from inbound approach to outbound departure, with months of observing time to gather detailed data. That wealth of data made Borisov the best-studied interstellar object to date until now. Enter 3I Atlas. In some ways, it's more similar to Borisov than to Oumuamua. It's clearly a comet, displaying the expected behavior of outgassing and developing a detectable coma as it approaches the sun. The detection of hydroxyl gas confirms the presence of water, which fits with our understanding of comets as icy bodies. But 3I Atlas brings something entirely new to the table: its extraordinary age. Neither Oumuamua nor Borisov provided clear evidence about their ages. We know they're not from our solar system, so they are presumably at least as old as the time it took them to travel here from wherever they originated. But we had no way to determine if they formed a few 100 million years ago or several billion years ago. Their surfaces had been altered by billions of years of cosmic ray exposure, making it difficult to read their formation history. 3I Atlas changes that. Preliminary data suggests an age range of 3 to 11 billion years, with a median estimate around 7 billion years. That makes it measurably older than our entire solar system and potentially one of the oldest objects ever studied up close by human instruments. This age distinction fundamentally changes what 3I Atlas represents. Oumuamua was a mystery, a puzzle we couldn't solve. Borisov was a familiar face from a foreign land, reassuringly similar to what we know. But 3I Atlas is a living fossil, a survivor from an earlier epoch of the universe, carrying within it information about cosmic conditions that existed before our world was born. It's not just different in origin, it's different in time. It connects us to the ancient universe in a way that no other object we've studied can claim. Think about the scientific implications of that. When we compare 3I Atlas to Borisov, we're not just comparing two comets from different star systems. We might be comparing comets from different eras of galactic evolution. The galaxy's overall chemical composition has changed over time as generations of stars have lived, died, and enriched the interstellar medium with heavier elements. A comet that formed 7 billion years ago formed from material that had been through fewer cycles of stellar processing than a comet that formed more recently. That difference should show up in subtle ways in the isotopic ratios, the relative abundances of various elements, and the types of complex molecules present. Current evidence indicates that even within our own solar system, bodies that formed in different regions show measurable chemical differences. The asteroid belt, the Kuiper belt, the Oort cloud. Each region has a slightly different signature reflecting the specific conditions that prevailed there during formation. Now imagine extending that principle across billions of years and thousands of light years. Every interstellar visitor is potentially a data point in mapping how planetary system chemistry has evolved across cosmic time and galactic space. Oumuamua gave us one confusing data point. Borisov gave us a clearer but still singular reference. 3I Atlas adds a temporal dimension, showing us what a very ancient comet looks like and how it compares to younger examples. And here's what excites me about the future. We're just beginning. 3 confirmed interstellar objects in 8 years might not sound like much, but it's enough to start seeing patterns and asking deeper questions. Studies propose that as our detection capabilities improve, we might discover that interstellar objects pass through the inner solar system several times per year. Most will be faint and difficult to study, but some will be bright enough to analyze in detail. Each one will add to our growing catalogue of interstellar visitors. Each one will carry unique information about its origin, and gradually we'll build up a comprehensive picture of what's out there in the vast spaces between stars. Imagine what we might learn from the next 10 interstellar objects we detect. Will some be older than 3I Atlas? Will some be younger? Perhaps even from star systems that are still forming planets? Will we find objects with completely unexpected compositions, challenging our models of planetary system formation? Will we finally solve the mystery of Oumuamua by finding similar objects we can study more thoroughly? Every new visitor is a gift, an opportunity to learn something we couldn't discover any other way. And 3I Atlas, with its ancient pedigree and measurable age, has set a new standard for what we should be looking for and what questions we should be asking when the next messenger from the interstellar void comes calling. There's a question I keep coming back to, and I suspect if you've made it this far in this journey with me, you're thinking about it too. What does all of this mean? Not just scientifically, not just in terms of what we'd learn about comet formation or galactic chemistry. But fundamentally, what does the existence of 3I Atlas mean for us as humans, for our understanding of our place in the cosmos, and for the future we're building toward? Let me start with the most immediate practical implication. 3I Atlas proves that our solar system is not isolated. We've known intellectually for a long time that we're part of a galaxy containing hundreds of billions of stars. That those stars have their own planetary systems, that material is constantly being exchanged between stellar systems over vast timescales. But knowing something intellectually and experiencing it directly are two very different things. When you see an object that was born in another star system billions of years ago, now passing through our neighborhood, that intellectual knowledge becomes visceral. It becomes real in a way it wasn't before. And that realization should change how we think about our solar system and our future in space. For decades, space exploration has been focused almost entirely on destinations within our solar system: the Moon, Mars, the asteroid belt, the moons of Jupiter and Saturn. These are challenging goals that will take generations to achieve, but they're at least conceptually within reach, using foreseeable technology. Interstellar travel, on the other hand, has remained firmly in the realm of science fiction. Something we can dream about, but that seems impossibly distant, requiring technological breakthroughs we can barely imagine. But interstellar objects like 3I Atlas provide a bridge between those two domains. They bring the interstellar realm to us. Instead of having to travel light years to study material from other star systems, we can wait for that material to pass through our neighborhood and study it here. That's not just convenient, it's transformative. It means that even before we develop the capability to send probes to other stars, we can begin answering fundamental questions about what those distant systems are like, what chemistry they harbor, what conditions prevailed during their formation. Researchers theorize that with better detection and tracking, and with improved rapid response capabilities, we might eventually be able to send probes to intercept interstellar objects while they're still in our solar system. Imagine a mission that launches to rendezvous with an incoming interstellar comet, landing instruments on its surface, drilling cores to sample its interior, even returning samples to Earth for detailed laboratory analysis. That mission would be technically challenging, but it's within the realm of current or near future technology. It's vastly easier than sending a probe to another star system, yet it would yield similar scientific rewards, direct physical samples from another stellar system, analyzed with the full power of Earth-based laboratories. And if we can do that, if we can routinely intercept and study interstellar visitors, then we'll build up a catalog of knowledge about the galaxy's diversity. We'll learn which elements and molecules are common across different systems and which are rare. We'll understand how planetary formation processes vary depending on the parent star's mass, composition, and environment. We'll trace the evolution of galactic chemistry across billions of years, all without ever leaving our cosmic neighborhood. That's the promise that 3I Atlas represents, a new way of exploring the galaxy, one that uses the galaxy's own dynamics to bring distant worlds to us. But there's a deeper, more philosophical dimension to this that I think is equally important. The existence of 3I Atlas, an object older than our solar system, wandering the galaxy for billions of years before arriving here, confronts us with the reality of deep time in a way that few things can. We live such brief lives. Human civilization in its entirety spans maybe 10,000 years. Our species has existed for a few 100,000. Even the most ancient human ancestors, the earliest primates, only go back tens of millions of years. Those timescales feel long to us, but they're nothing compared to the age of 3I Atlas. This comet existed for billions of years before the first human ever looked up at the sky. It was already ancient when Earth was forming. It was old when the first life appeared in our oceans. It had been traveling through space longer than our planet has existed by the time the first civilizations arose in Mesopotamia and Egypt. And it will continue traveling long after our civilization has faded, after our species has evolved into something unrecognizable or gone extinct, after the sun has entered its red giant phase and consumed the inner planets. 3I Atlas, if it doesn't collide with anything, could persist for billions more years, carrying its ancient secrets onward into a future we can't imagine. Confronting that kind of timescale does something to your perspective. It makes the concerns of daily life seem simultaneously trivial and precious. Trivial, because in the vast sweep of cosmic time, none of it matters. No empire, no achievement, no crisis will leave even the faintest trace billions of years from now. But precious because despite that cosmic insignificance, this is the life we have. The brief window of awareness and experience that's been granted to us. The fleeting moment when we get to participate in the universe's unfolding story. And here's what I find profoundly moving. We're the first humans who can recognize objects like 3I Atlas for what they are. Our ancestors saw comets and were terrified or awed, interpreting them as omens or divine messages. Even a century ago, we lacked the tools to identify an interstellar visitor. But now, in this peculiar moment in history, we've developed both the technology to detect these objects and the scientific framework to understand them. We can look at 3I Atlas and really know, that we're seeing something older than our world from another star system, carrying information about the ancient universe. That knowledge is a gift. It's a form of understanding that no previous generation could access. What do we do with that gift? That's the question that haunts me. Current evidence indicates that we're living through a unique transition period in human history. We're advanced enough to detect and begin studying interstellar objects, but not yet advanced enough to explore them thoroughly or to protect ourselves from potential cosmic threats. We can see the universe with unprecedented clarity, but we're still confined to one fragile planet, vulnerable to any number of existential risks. In that sense, objects like 3I Atlas serve as reminders of both our capabilities and our limitations. They show us how far we've come and how far we still have to go. Studies propose that within the next century, humanity will face fundamental choices about its future. Will we remain a single-planet species vulnerable to any catastrophe that befalls Earth? Or will we expand outward, establishing permanent presences on the Moon, Mars, and eventually other bodies in the solar system? Will we develop the technology to mine asteroids, harvest energy from the sun at scales that dwarf our current consumption, build rotating space habitats that support thousands or millions of people? Will we eventually develop the capability to send probes and perhaps even crewed missions to other star systems? These aren't just science fiction fantasies anymore. They're increasingly serious discussions among scientists, engineers, and policymakers. And discoveries like 3I Atlas feed into those discussions by expanding our awareness of what's out there, what's possible, and what might be waiting for us in the wider galaxy. Every interstellar visitor teaches us something about the cosmic environment we'll eventually venture into. Every measurement we make, every chemical signature we detect adds to our understanding of what we'll encounter when we finally do leave our solar system and begin exploring the interstellar ocean. But perhaps the most important implication of 3I Atlas is the simplest. It reminds us that we're part of something much larger than ourselves. The atoms in your body were forged in the cores of ancient stars. The water you drink has cycled through countless clouds and oceans over billions of years. The oxygen you breathe was produced by living organisms over geological timescales. And now we know that even our solar system isn't a closed system. It's part of a galactic ecosystem where material is constantly being exchanged, where ancient wanderers from distant stars pass through our neighborhood, where the chemistry of life is potentially being distributed across light years by processes we're just beginning to understand. That interconnectedness should change how we think about ourselves. We're not separate from the cosmos, observing it from the outside. We're participants in its unfolding. We're made of its materials. We're governed by its laws. Our consciousness, our ability to understand and appreciate the universe, is itself an expression of cosmic evolution atoms, arranged in a pattern complex enough to contemplate their own existence and origin. And when we look at something like 3I Atlas, we're engaging in a kind of cosmic conversation, a dialogue between the ancient universe and the contemporary mind, mediated by light and mathematics and the scientific method. I want to pause here and make an important clarification about language. When I speak poetically about cosmic conversation or the universe speaking to us, I'm using metaphorical language to describe how science works, not making a literal claim that the universe is conscious or intentionally sending us messages. This is a crucial distinction. Literally and scientifically, the universe operates through physical laws, gravity, thermodynamics, quantum mechanics, electromagnetism. The Three-Eye Atlas follows these laws naturally and indifferently. Our understanding of it is our interpretation of those natural processes, not communication from a conscious cosmos. The poetry is real. Recognizing ourselves as part of a vast cosmic story is profound. But that profundity comes from understanding actual physics and chemistry, not from attributing intention or consciousness to the universe. Both perspectives inspire awe, but only one is grounded in evidence. When I invite you to feel that connection across cosmic scales, I'm inviting you to appreciate the genuine science and actual physics that connects us, not to imagine that something is deliberately reaching out to us. Do you feel it? That sense of connection across inconceivable distances and timescales. That's not mysticism. That's not wishful thinking. That's the reality of what modern astronomy reveals. We are connected to Three-Eye Atlas, to the star system where it formed, to the ancient cosmos where that system arose by chains of cause and effect that stretch across billions of years. The same physics that governs that distant comet governs every cell in your body. The same chemistry that created its ices created the water in your cells. The same cosmic evolution that produced its parent star produced our sun. We're branches of the same immense tree, and recognizing that should fill us with both humility and wonder. This is why Three-Eye Atlas matters, not just because it's scientifically interesting, though it is. Not just because it's older than our solar system, though that's remarkable, but because it's a tangible reminder of our place in the cosmic story, a messenger from deep time that tells us we're part of something vast, ancient, and ongoing. And that message, if we're wise enough to really hear it, might be exactly what we need in this moment of our history. A perspective that transcends our immediate concerns and connects us to the longest, deepest narrative. There is the story of the universe itself, unfolding one moment at a time with us as both observers and participants in its next chapter. So, here we are. We've traveled together through the story of Three-Eye Atlas, its impossible age, its billion-year journey through the galaxy, the water it carries from an ancient star system, the brief window we had to observe it before it fades back into the darkness. We've compared it to the other interstellar visitors that have passed through our solar system, and we've explored what it means for our understanding of the cosmos and our place within it. But I want to end with something more personal, more immediate. I want to talk about what you do with this knowledge now that you have it. Because here's the thing, you're living in a time that future generations will look back on with envy. You're alive during the first few years of humanity is awareness that interstellar objects regularly visit our solar system. You're part of the first generation that can look up at the night sky and really know that some of the faint points of light occasionally passing by are ancient wanderers from other stars carrying secrets from the deep past. That's not just interesting trivia. That's a fundamental shift in human consciousness, and you're witnessing it in real time. What strikes me most about this moment is how easy it would be to miss its significance. Three-Eye Atlas isn't making headlines the way some discoveries do. It's not landing rovers on Mars or taking photographs of black holes. It's a relatively faint comet that most people will never see, even with binoculars. And its moment of visibility is already passing. By the time most people hear about it, if they hear about it at all, it will already be leaving, fading back into the cosmic darkness from which it emerged. And yet, this quiet visitor carries within it more history, more distance, more cosmic perspective than almost anything else humans have ever studied. That disconnect between the magnitude of what Three-Eye Atlas represents and the relatively little attention it receives says something about how we filter reality. We're drawn to the immediate, the dramatic, the visual. But some of the most profound truths are subtle, require patient explanation, reveal themselves only to those willing to look carefully and think deeply. Three-Eye Atlas is one of those truths. It won't change your life tomorrow, but if you let it, if you really absorb what it represents, it can change how you see the universe and your relationship to it. So what do you do with that? First, share it. If this journey we've taken together has moved you, sparked your curiosity, or shifted your perspective even slightly, then talk about it. Tell someone about the comet older than our sun that's passing through our solar system right now. Explain why it matters. Help spread the awareness that we're living through something remarkable, even if it's happening quietly. The more people who understand the significance of discoveries like this, the more support there will be for the telescopes, the missions, the research programs that make these discoveries possible. Second, stay curious. Three-Eye Atlas won't be the last interstellar visitor. More are coming, and with each one, we'll learn something new. Pay attention to the discoveries as they happen. Seek out the stories behind the headlines. Ask questions. Think deeply about what these cosmic messengers are telling us. The universe is speaking to us through objects like this, offering us glimpses into its deep history and vast geography. But we only benefit from that gift if we're paying attention. And third, let it change you. Not in some dramatic way necessarily, but in the quiet way that genuine understanding changes a person. Let the knowledge that you exist in a universe billions of years old, where ancient objects from distant star systems pass through our neighborhood, inform how you think about time, significance, and connection. Let it give you perspective when life feels overwhelming, when problems seem insurmountable, when you forget that you're part of something much larger than your immediate concerns. Three-Eye Atlas has been traveling for longer than Earth has existed, and it will continue traveling long after we're gone, indifferent to our existence and yet profoundly connected to the same cosmic story we're part of. This is the gift that astronomy offers. Perspective that transcends the human scale, connection that spans the cosmos, wonder that never exhausts itself because the universe is always revealing new layers of complexity and beauty. Three-Eye Atlas is one small piece of that larger gift, but it's a perfect piece, ancient, mysterious, tangible, and yet almost impossibly distant in time and origin. So, here's my final question for you, the one I want you to carry with you after this video ends. Do you think Three-Eye Atlas's age tells us something we're not ready to accept about the universe? I don't have a definitive answer to that question, and I'm not sure anyone does. But I think it's worth asking, worth pondering, worth discussing, because in the asking, we open ourselves to possibilities we might otherwise miss. And in this moment of human history, when we're just beginning to reach outward and understand our place in the cosmos, remaining open to those possibilities might be the most important thing we can do. Thank you for taking this journey with me. Keep looking up, keep asking questions, and remember, we're the lucky ones. We get to witness this ancient messenger's passage. We get to know what it means. And that knowledge, that awareness, is a privilege that connects us to the deepest mysteries and the longest time scales the universe has to offer. Don't let that pass you by unnoticed. The cosmos is revealing its history. Will you seek to understand,